On the other hand, if you want me to answer by email, it's okay. Let's send me an email here. Okay, guys? Okay, so this one is for the tutorial number 1. And we are working on the tutorial number 2. About the tutorial number 1, do you get any trouble? No? You feel clear?
No, we don't.
For all the thing in the first tutorials? So it's look good? Okay, so let's start. In the second chapter, okay, actually it starts from the lecture number 4 of form. So at this part, you will make familiar with the atoms. This means you will have to study about the structure of atoms. Okay, different type atom appear for one element. For example, you will have a set of of atom have the same number of proton but different numbers of neutron. Okay, in that case, you will have isotopes. The set or the set, yeah, a class of the elements, a class of atom we call the isotope, have the same number of protons but different numbers of neutron or different numbers of atomic mass. Okay. So in this one, now you were introduced about the structure of atom. It means the atom will contain several things. We call subunit of atom, right? So an atom will contain a nucleus, right? An atom always contains a nucleus. And then electron moving around. Okay, so this guy is namely electrons with the denote as E, with the minus symbol. Okay, this guy is namely nucleus. So the nucleus will contain a proton and neutron. Okay, so the guys, electrons, will contain the charge of the -1, okay, or negative charge. Proton contain charge of +1, and neutron contain charge of 0. Okay, and in the normal atoms or neutral atoms, why we call it the neutral atoms? Because of the number of electrons always equal to number of protons. Okay, so if you have 5 protons of that atoms, you will have 5 electrons. So 5 negative and 5 positive, they will neutral together or cancel together to form an atom with the charge of 0. It's okay. So in that case, we will call this guy is a neutral atom. Okay. So let's move to the first exercise. Questions. Do you send your homework to Miss Ngọc?
Yes, we are.
Yes.
Yes. Okay. Perfect. So let's move to the first tutorials or first exercise. Okay. So in this exercise, let's close it. In this exercise, they say that you have a charge or a particles with charge, okay, go through a 2 electrical charge plate, okay. Sometimes we can call this one an electrode. Okay, so you see when the charge goes through an area between 2 electrodes, you will see that charge or that particle move in a curve. All the movements pathway of the charge is bent. Okay, so what is the reasons? Anyone can help me to answer it? Anyone can help me to answer why the charge particles here, or the movement of the charge particles here, is bent? Guys, be patient. Sorry, be confident and say to me.
We raise hand to.
Actually, you can tell me because of I am opening the slide screen, so I will not see your raising hand. Okay. So let's just turn on your microphone and answer. Okay. Mr. Quang Vinh.
Yes. The part of the charged particle bands will bend because it is repelled by the negative charge plate and attracted to the positive charge plate. Okay.
So normally, if you don't have any charge, thank you, Vinh. If you don't have any charge, right, the particle, because of they are moving this way, so they will move this way. Okay, go in the straight line. The thing to make the particle bend because of the interaction between negative, positive charge with the charge of the particle, right? And we see normally positive charge will like to attract negative charge, right? So in that case, the particle bend to the positive electrode. It means that the attraction between the positive charge here and the particles is either the attraction is not repulsion. Okay. So in that case, we can say that particles will contain a negative charge and it will be attracted by positive charge. Okay. In another side, negative charge and negative charge, they don't like together. We call this one is repulsion. Okay, so they also say to you that with the electrode, the negative electrode, they don't like the particles because they have the same charge, and then the particle will be repulsed to go farther from this electrode, or they have to bend this way. Okay. And by that, you also answer B, the side of the electric charge of the particle is negative. Okay. Okay, the next question. If you increase the charge here, what do you think? Is bend increase of bending, decrease of bending, or stays the same? Of course, when you increase the charge, the negative charge, the attraction force between the positive and negative will increase, right? We call this one Coulomb Force, right? So by that way, normally the force increase will let the particles bend more. Okay. In another thing, in what case do you think that if we increase, for example, now we increase the charge, the negative charge here to 2 times, okay? In what case you will have that charge or that particle stays the same in bending. It has to answer. Okay, so let's move this way to explain to you. Okay, so we have the charge is moving straight like this. Okay, and when they go through two electrode, this one will move this way. Okay, so the movement here can be separated into, when you project this movement into the standard, how to say, I just forget the word, to a standard system. Okay, we can separate them into two forces applied to the movements. Okay, this one can be considered as a force, and this one can be considered as the energies of the momentum or linear momentum. Okay, or P. So this one will be two vectors of force and momentum. So bad thing. It's okay. So now, if we have a higher force, the force here increase. If we let the particles move this way, right? And if we have the momentum of the linear momentum increase, they will bend this way. Okay, or less bend. So the force in the vertical direction here will be named the Coulomb force. And this one will relate to the interaction between the negative and positive charge. Okay. It's okay. So it means that if you increase the charge of the particles, or you increase the positive charge of the electrode, okay, now you will increase the interaction between the electrode and particles. So by that way, you will increase the Coulomb force. Okay, and then they will move this way or more bend. Okay, so now to keep this one, if let's consider now you are increasing the charge, but you still want to keep this guide stays the same. It means that you have to increase the linear momentum too, right? The linear momentum P is normally calculated by mass multiplied to the velocity, the vector of the velocity. It's okay. So by that way, if you want to increase the linear momentum, you have to increase mass or increase velocity of the particles. It's okay. So this one is also help you to answer the next questions. If the mass of the particle increase, okay, the mass increase here, it led you to this one increase, more linear momentum increase. Okay, the speed of particle remains the same. The speed remains the same. Okay, it's not changed. you only increase the momentum here. You not change the speed, okay? The charge is not changed, okay? So now you will let the particles go less bend, okay? So we can say that in this one, the charge increase, the bending increase, but the mass increase led to the charge decrease. Okay, that's the bending decrease. Okay, do you understand it? Okay, let's move to the exercise number 2. Anyone want to give me the answer?
Only the answer.
Sorry?
Okay, for question A, the percent abundance of red spheres, which are 293 or 60%, and
60%.
the other one 40%.
Okay, so it's very simple, right? So in this exercise, there are several things you should understand to me. Okay, firstly, what is the percent of abundance, or the percentage of abundance? The percent of abundance is ratio of amount of mass of an isotope to the total mass of substance. Okay, so in this one you have a two type of the elements. Nevadium, okay, this one is a fiction elements, it's not real. Okay, this one is shown to you about the 293 of the atomic atomic mass, and this one is 295 of the atomic mass. Okay, so these colors, red and blue, to show to you about the numbers of atoms will have a different mass or different type. Okay, two of them, when you have a different mass, atomic mass like this, but have the same numbers of protons, you will have the word isotopes, right? So to define the percent of abundance of an isotope, 293, for example, compared to the others. Okay, so now you have to count the numbers of atoms. Sorry, it's not really clear. I take this one from a papers, but not really right. The ratio of the amount of atoms, total atoms. Okay. So now you will see in the total atom of a substance, like in the square here, you have 20 atoms, right? The red one will take to you 12 pot, right? Or 12 sphere. So the percentage of abundance will equal to the number of atoms of a particular isotopes. Okay, so you have an abundance of NV 293 will equal to 12 over 20 multiplied to 100%. Okay, and this one is 60%. Okay, in another side, you will have A of 295, nevadium will be equal to 8 over 20 multiplied to 100% and is equal to 40%. Okay, so by that way, you can calculate the percent of abundance of each elements or each isotopes. Okay, and to define the atomic weight or average atomic mass of nevadium, you have to use the equation here or expression here. Okay, this one is the total of the atomic mass multiplied to the percent of abundance of that isotopes. Okay, and divide to the 100%. Okay, so in this one, average atomic weight of the nevadium will be 293.15, right? Multiplied to 60 plus 50, right? Multiplied to the 40 and divide to 100. And the result will be anyone give me the result, please? No?
Down is 293.95.
293.95.
0.95
Okay.
AMU.
Okay. Can you tell me why you take two values after the commas here?
I think I follow the rules of the significant figures.
The rule of significant figures. Are you sure? In the significant figures, normally you have to, when you do the multiplication, you have to choose the one who have the lowest number of significant figures, right? Yes, right? And then you see, this one you have only one significant figures. Why you have a 5 significant figure here? It's okay, so this one is just make you a little bit confused. Okay, so now let's help me to understand. Significant figure is only the way to calculate or calculation of something complicated from 200 or 300 years ago. Okay, at that time they don't have any calculators, so they have to round up, they have to limit the number of significant figures, okay, to make the calculation become easier. But now you have a phone, you have calculators, you have a laptop, and you can calculate anything with very, very precise numbers, very precise results. Okay, so in that case, don't care too much about significant figures. Let's understand why we use significant figures, okay, and understand also the rule to apply significant figures. But you don't have to follow the significant figures all the time. Okay, the significant figure actually is important in case you have to read data from the experiments. When you balance something, for example, you have to follow to the rule of significant figures to understand exactly the change of the mass in any kind of measurements. Not really important in terms in case you have to calculate anything. Okay. Very simple. right? The exercise is very simple. I could say that. The next exercise related to the ionic compounds and molecular compounds. So anyone can, okay, so I write it here. So ionic compounds normally get generated in this moment. Let's understand the ionic compounds normally form between metals and non-metals, okay? And molecular compounds normally form between non-metals, okay? So let's understand these moments. When you study about the bonding, you will be more clear about the ionic bonds, molecular bonds, okay? So the difference between the ionic compounds and molecular compound is what you see on the graph 1, 2 here, okay? Why ionic compounds normally the atom will stay in order like that, but molecular compounds they go freely like that, okay? So let me explain. Ionic compounds normally generated between a metal and non-metal. Okay, so you see in this one, you will have a process of sodium chloride to form sodium chloride. Okay, so the thing is, one sodium atom prefer to donate 1 electrons to chloride. Okay, so at the very first moment, you will have a sodium become sodium plus, chloride will become chloride minus. Okay, and now you will have a positive charge and negative charge, and they attract together. Okay, they attract together. So by that, you will form sodium chloride. Okay, the thing in this case is sodium with positive charge and chloride with a negative charge stay close together. But the sodium here still can attract another chloride. Okay, so you will have another chloride stay very close to the sodium, and the same, the chloride with the negative charge, they are not only attract the first or the original sodiums, they can attract another sodium too. Okay, and with each sodium plus and chloride minus there, they will not attract only one sodium or chloride. They attract many sodium and chloride. Okay, so you will see if this one contains a negative charge, this guy contains a positive charge. A positive charge here can attract another negative charge. Okay, and one negative charge can also attract several positive charge. Okay, so because of that phenomenon, electrostatic force, ionic compounds normally will be formed or generated as the crystal with the arrangement of atoms in order. Okay, because this one is an order. Sorry. Okay, let's move to the molecular compounds. Molecular compounds normally contain or generated between non-metal, water for examples, okay, hydrogen for examples, okay, nitrogens, methane for example, okay, they generated between non-metals. So in the part of bonding, you will study more clear about that. But in this case, you will see in the process of making molecular compounds, the electron will not move from one atom to the other atoms. They are not moved like the case of ionic compounds. So they led you to a thing or to a thing that you will not have a very, very clear positive charge or negative charge in case of molecular compounds. Okay. And when they don't have a clear positive charge, negative charge, it means that they will not attract the other positive charge and negative charge, like the case of ionic compounds. Okay, so by that way, the molecular compound will not have a very strong interaction to make an order arrangement like the ionic compound. Okay, so you will see the different molecule of the molecular compound sometimes can go free like this, okay, especially for the case of gases. Okay, and you will also study that the molecule, even the molecular compounds like water, for example, okay, like a water, for example, actually you still have a difference between the electronegativity between oxygens. This guy will attract electrons. Oxygen will attract electron from hydrogen. So the electron density stay on the oxygen is a little bit higher compared to the electron density on hydrogens. Okay, so you will have a little negative charge stay on oxygens and a little positive charge will stay on hydrogen. It's not clear. It's not clear negative or positive, one negative like the ionic compounds, but they still a little positive and negative. Okay, so it means that you have a, we call a vector of polarity on the hydrogens, negative, positive. Okay, so even the negative or the polarity of hydrogen of the water is quite small like that, but they still can keep the molecule of water stay quite close together. Okay, and then you see this is the reason why water stay as the liquid at room temperatures, but nitrogens, they don't have the polarity and they don't have the interaction together like that. So nitrogen stay at gas at room temperatures. Okay, so in some of the next lectures, I think you will know the molecules of ionic compounds or ionic bonds. Okay, covalent bond. Okay, polar covalent bond or non-polar covalent bond, and then you will study about the polar molecule or non-polar molecule. Okay, and the interaction of the structures of that molecule in that case will help you to explain a lot of properties, especially the physical properties of compounds. Okay, so now you will see this one will be ionic compound and this one will be molecular compound. Okay, the next exercise related to the Danton atomic theory, right? At the time of Danton's, actually they still don't have still don't have a very clear about the definition of atoms. Okay, so Danton or John Danton with some of chemists at that moment, they only know or they only have a theory that the matter combined with matter in defined quantities or multiple of the quantities. Okay, it looks like you have the matter A, okay, combined with matter B. Okay, so you will have one guy we call AB, for example, Okay, in the very first moment, you will have 1 gram of A, 1 gram of B to form AB. Okay, in another side, if A and B can form another compounds, you will have in the second case, you will have 1A need to combine with 2B or 3B to form AB2, AB3. Okay, and the Danton theory is the mass of B in the second case will be integral times of the mass of B in the first case. Okay, this one is the Danton theory. Okay, so in this exercise number 4, you have to calculate the mass of oxygen per gram of nitrogen. Okay, now you have the mass of nitrogen here and several values of mass of oxygen to form 4 different compounds. Okay, so the first question, calculate the mass of oxygen per gram of nitrogen. I will not say about that. Okay, anyone can give me the result, please. Let's call the compound the first, the second, the third compound, and the fourth compounds. Okay, so anyone can give me, with the first compound, you will have the ratio between oxygen and nitrogen is?
And it is equal to 0.571.
Is it 0.571? Okay, right, thank you. The second one?
And the second one is equal to 1.14. 1.14. Yes.
Just it?
Yes. Yes.
Okay. Can you give me more detail? A little bit more detail. So okay, no problem. Number 3.
Number 3 is equal to 2.28.
Okay. And the next?
It is equal to 2.85.
2.85.
85.
Okay. So I have a small suggestion to you. Okay. When you read the numbers after the comma, okay, don't say 14, don't say 28, don't say 85. Okay.
Yes.
After the comma, let's read the numbers one by one. For example, this one will be 1.14, 2.28, 2.85. Okay, because of actually this one is stay after the comma. If you have the values before the comma, it becomes 14. Okay, if this guy is 14 point something, this is really 14, but this one is stay after the comma, it's not 14 anymore. Okay, so let's read it 1.14, 2.28, something like that. Okay, guys?
Yes. Thank you.
So the question B, how do the number in part A support Danton atomic theories? Okay, as you see, Danton theory, I explained to you, if A connect with B, okay, A react with B, for example, to form AB in the first case. In the second case, if A react with B to form another compound, the amount of B in the second case and will be integral times of the amount of B in the first case. Okay, so now you can see, if we consider this one is the 1, okay, in the second compounds, you have the mass of oxygen will be 2 times of the first case. Okay, in the C, or in the third compound, the mass of oxygen will be 4 times of the first case, and in the last one, it will be 5 times of the first one. Okay, so now you will see integer terms, and integer terms. So they support the John-Dalton theory by the ratio between oxygens or amount of oxygen in different compounds. Okay, guys? You understand about that?
Yes, teacher.
Okay. So the next one will relate it to the gold atoms, right? Oh, how many exercises do you have? 18. It's okay. So I think I have to increase a little bit the speed. So I will skip some exercise if it's too easy to you. It's okay. If you see some exercise too easy, let's stop me and we can move. Okay, so actually this exercise I would consider is a very simple exercise. Okay, so I want to introduce you a little bit related to the gold nanoparticles. Okay, so if you have the gold nanoparticle with different size or different diameter, gold nanoparticles like this, 20 nanometers, 30, 40, 50 nanometer, you will see the colors of the solution of gold nanoparticles in water will change. Okay, so some of the gold nanoparticle with the size of a little bit more than 100, about 110 nanometer, will give you the color of purple and blue. Okay, if you have a smaller gold nanoparticle, like just several nanometer, the solution become a very light red. Okay, and even they are smaller, they become yellow. So actually, you can see a lot of color come from gold. Okay, it's not like the ring you are wearing, if you have ring. Okay. So this one based on the phenomenon we call a surface plasmon or surface plasmonic phenomena of gold nanoparticles. And okay, it's quite funny for the guys who work in the department of material science. Okay, so if you have time, let's take a look on this one. It's quite interesting. Okay, you see the surface plasmonic phenomenon. Okay, so the question A here, expressed in nanometer and picometer is simple, right? So you have 1 meter will equal to 10 power minus 3 millimeter, right? Equal to 10 power minus 6 watt, guys. Do you still remember? Micrometer equal to 10 power minus 9. Nanometer equal to 10 power minus 12 picometer. And this one also equal to 10 power minus 10 angstrom. Okay. So if you have these values in angstrom, now you can move them into the nanometer and picometer, no problem. Okay. And after that, if you have to arrange gold atoms line up in a span of 1 micrometer. So you have a micrometer like that. You arrange gold nanoparticle there. So it's very simple to you to calculate how many gold atoms will stay there, right? And for the last questions, we related to the calculation of the volume of a sphere. Okay, so the volume of a sphere will be calculated by the expression of, anyone remember and tell me? The volume of the sphere. How can you calculate the volume of a sphere?
The volume of sphere is equal to 4/3 multiplied with pi multiplied with the radius cubic.
Okay, so just it. Very simple, right? Okay, be careful with the different unit, centimeter, millimeter, picometer, nanometer, and so on. Okay, just it. For this exercise, very simple. Next one, weak one isotope. Okay, so isotope, as I said to you before, isotope is the atom of the same elements. So if they are the same elements, firstly, the symbol of element will be the same. Okay, why I have to say about something very simple like that? Because of last year, a lot of you, many of students still make wrong in this very simple question like this. Okay, isotope are the same elements. So the same element have the same symbol. Okay. The second thing, isotope will have a different mass. Where is the mass? The mass on the symbol of element is here. Okay, the upper values. The lower values will be the atomic numbers. And normally, if you have the same symbols, you will have the same atomic numbers. Okay, so by that, of course, this one is wrong. This one, right, right. Okay. The question number 7 related to how many proton, neutron, electrons. So this one is very, very simple. Okay, to define how many proton, neutron, electrons, let's consider. Firstly, you have a symbol. Okay, so from the symbol, let's define the position of that atom in the periodic tables. So you will see it here. Argon. Okay, the values on the periodic tables, this guy will give you the numbers of proton and electron. Okay, so in this one you will have a number, the number of electron equal to the number of protons and equal to the atomic numbers. And atomic numbers, of course, will be this one. Argon will have 15 in atomic numbers. Chloride will have 17 in atomic numbers. Okay. From that, to calculate the number of neutron, you have to take the atomic mass and suppress the atomic number. Okay, so for examples, the first case, argon here with the mass of 14. So you will have a number of electrons equal to number of protons and equal to 18. Okay, the numbers of neutrons will equal to 40 minus 15 and it's equal to 22. Okay, So let's do the same thing with the other. Very similar to that exercise is exercise number table to do that. Okay, the first one, if you have a symbols of 79 bromium, so you can find the symbols here. You see the bromium. Okay, so from the bromium you have the number of proton is 35. The number of electrons will be 35 too. Okay, the number of neutrons will be 79 minus 35. Okay, and you will get 44 in neutrons. Okay, and the mass will be 79. Okay, so let's do the same for the other. For the second one, you have a proton of 25. So number of electrons will be 25 too. The number of proton and electron is the atomic numbers. So let's find the elements at the position of 25. And you will get the symbol here is the magnesium. Okay, the magnesium have the number of neutron is 30. So you will have the mass of this one will be 25 plus 30 is 55. So you have a symbol here is a 55 magnesium. Okay, so you can do the same for the other. Exercise number 9 will relate to the isotopes. You have to calculate the atomic weight or average atomic mass. So we have the expression to calculate it, right? So you have the average atomic mass of copper will be and for all of them divide to 100. So anyone can give me the results, please?
It is equal to 63.5456 AMQ.
It's okay. Very simple. Let's do the same if you have an exercise related to the isotopes. Okay, the exercise number 10 related to the similar thing. Okay, the first one related to the calculation of the average atomic mass. I will not calculate it. Okay, I will not calculate it. Question B is get the mass spectrum of magnesium. Okay, mass spectrum of magnesium is come from a technique we call a mass spectroscopy. Okay, or MS. So normally we will not use MS to calculate or to define the mass of different abundance, different isotopes like that. Okay, but the mass spectroscopy, these questions get the mass spectrum of Mg will be exactly the same things which you see on the mass spectroscopy or mass spectrum of any other kind of molecules. Okay, so the mass spectroscopy technique is based on an idea. You have a samples here, okay, and then you use some of the energy like heat, temperatures, lasers, okay. So by that way you can modify or change or break the molecule to become an ionic state, okay, an ionic state. So after that the ionic state or ions can go through an accelerator, okay, and then they will go through two electrodes, or in that case it's a magnetic field. Okay, so you see, because of the ions contain a charge, okay, so normally they will be bent when they go through a magnetic field, okay, similar to the first exercise, and after that they will impact to the detector here. So by define the time of movement from this position to the detector, the first type, or define the bending, okay, define the different bending of different particles from the samples. Now you can define the mass of each particle. Okay, so it's the main idea of mass spectroscopy. So by that way, you will have a diagram or mass spectrum like that. Okay, on the vertical axis, this one will be the abundance, and in the horizontal axis, you will have a mass to charge ratio. Okay, so the abundance and the position of the mass will be shown in kind of column of the column diagram like this. Okay, so in the case of magnesiums, you will draw the same things. Okay, this one will be the abundance. Okay, this one will be mass. So you have only three types of or three isotopes of magnesiums. So let's write here 24, 25, 26. Okay, actually you should write these values, but I don't have enough place to write it. So you will have let's call this one is 100, okay, and this one is 10. So you have a 25 is around 10, 26 is around 11, a little bit higher, and for the 24 it will be 79. It's here. Okay, so you can write the values of the abundance. And just it. Okay, so this one is the mass spectrum of magnesium. Okay, so for the word, you may feel confused to the word mass to charge. Okay, so this one please follow to the course if you want to know. Please follow to the course of mass spectroscopy or some of the equipment characterization of materials. Okay, this one is easy. I don't have time to explain why it's become mass to charge. Okay, the next one related to the define chemical symbols, right? The name of group with it belong, and it's metal, metalloid, or non-metal. So okay, so this exercise, let's I will have you to analyze the periodic tables, okay, to say to you about the position, different position of the atoms or different type of elements, okay. Okay, this kind of compounds, this is all the kind of element is shown on the periodic tables, okay. So the periodic table will say to you about firstly the symbol of elements, okay. Of course, they have the name of the element too. So the symbol of elements normally contain atomic numbers and atomic mass, okay. So based on the atomic numbers, the increase of atomic numbers, the elements will be arranged in the periodic tables. For example, they run from the atomic numbers of 1 for hydrogen to 2 for helium, 3, 4, 5, 6, 7, 8, something like that. Okay. So in the periodic table, you have some different colors here. It's okay. So for examples, this side or this part of the elements until around here. Okay. All that side. This one is a metal. Okay. This kind of element in that frame I was just right here are metal. Okay. So they can separate in several types. Like, okay, alkaline earth metal. This one. This guy is transient metals. Okay. The transient metals. Rare earth elements or sometimes rare earth metals like this guy. It's okay. In another side, you have from this one. Oh, sorry. It's okay. All of this part in this side we call non-metal. Okay. Non-metals. I'm sorry for a second. Okay, let's continue. The non-metal will contain something like carbon, nitrogens. Okay, they are the clear non-metals. Okay, so this one. So you see, we will have a little bit or several atoms like boron, silicon, arsen, tellurium. Sometimes we can consider polonium, stibbium, or antimony, germaniums. Okay, so there are several atoms here. Stay in between metal and non-metals. Okay, this guy is namely metalloid. Okay, so the kind of the element will have the property sometimes similar to metal. It's like a metal, but also like non-metals. Okay, so we call this one metalloid. So you can see this guy normally can be applied as the semiconductors for solar cell, for example, like a silicium. Okay. So when you have time to go to some of the solar cell or solar panel field in the middle of Vietnam, like in Ninh Thuận, for example, all of the solar panels there will be based on the technology of the silicon, okay, of the silicon. Okay, so you have also the last one like this. The last column here is namely noble gas. Okay, so based on that, you have to define this one, this one, this one, this one, and this one. Where are they on the periodic tables? And set them into metal, non-metal, or metalloid. Okay, again, this one is non-metal, and the other is metal. Okay. So okay, the next exercise related to the forming of ions in the chemical reaction of different elements. Okay, so the rule is, so let's take a look. If you have the element stay in the group 1, this guy will form the ions of A1 plus. Okay, if they stay in group 2, they will form A2 plus. Okay, if they stay on the group 3, this one is group 3A. So this one will form A3 plus. Okay, with group 4A, this one is a little bit complicated. Okay, sometimes they can form, normally they can form 4 plus. Okay, but sometimes they can stay at the 4 minus or 2 minus, something like that. Okay, in the reverse side, if you have a 7A, this one is namely 7A. This group 7A here prefer to form an ions 1 minus. Okay, 6A we form a 2 minus. This guy is the 5A we form 3 minus. Okay, so now let's take a look on the about this side. Okay, about this side, the transient metal. Normally transient metal have a lot of ions. Okay, for example, iron here, you will have an iron 2 plus, iron 3 plus. Okay, for the cobalt, for the cobalt you will have a cobalt 2, cobalt 3. Okay, for the chromium you have a chromium 2, chromium 3, chromium 4, chromium 6. So many. So at this moment, let's skip the transient metal. Okay, let's understand about 3 groups of metals. 1, 2, 3. Okay, and 3 groups of non-metal. 5, 6, 7. Okay. So magnesium stay on the group number 2. So the ion of magnesium will be 2 plus. Okay, aluminium stay on the group 3. So this guy will be aluminium 3 plus. Okay, potassium stay on the group 1. So you have a potassium 1 plus. Okay, sulfur stay on the groups 6A. So sulfur prefer to become 2 minus. Fluoride stay on the group 7A. So they prefer to become fluoride minus. It's okay. And similar thing for the other. Exercise number Steam, right? Do you have any questions, guys? Anyone can help me to explain why the guys stay on number 1, 2, 3, prefer to become or to bear the positive charge, but the other stay on number 6, 7, 8 here, prefer to become negative charge when they form ions. Anyone can explain?
I think they form ions because a form with a complete octet of electrons, like those in the noble gases group, are more stable. So the element will lose or gain electrons depends on which action would give a lower magnitude of charge. So, for example, natrium in the group 1.
This is sodium.
Sorry. Sodium in the group. I take the magnesium. Magnesium in the group 2.
Okay.
The coding
Electron configuration.
electron configuration is 1s2, 2s2, 2p6, and 3s2. So it has 2 electrons in the outer. At the outer, so it will lose 2 electrons, so it become magnesium 2+.
Okay, thank you very much. So he mean that in case of all the elements, okay, normally the element will prefer to become the most stable state. Okay, the most stable state. And in terms of periodic tables, normally the most stable state is the guy who have the electron configuration similar to this guy. Okay, the noble gases. So in case of magnesium, they have a 2 electron difference from the electron configuration of neons. Okay, a noble gas, neon will have a electron configuration of only this part. Okay, so magnesium prefer to donate 2 electrons different with neon. Okay, and by that way, magnesium will prefer to donate 2 electrons out and become magnesium 2+. Okay, get it? On the other side, in the case of sulfur, sulfur will have an electron configuration of 1s2, 2s2, 2p6, 3s2, and 3p4. Okay, so sulfur have electron of 2, 3p4, but the argons we have argons we have the same thing like this, but it's the 3p6. This guy stay in the noble gases, right? So sulfur only have a 2 electron different with argon. So sulfur prefer to get 2 more electrons to form a pair electron configuration of argon. Okay, so it's the reason why sulfur prefer to get 2 more electrons and become sulfur 2-. It's okay. Okay, so this is the reason why you will get the electron configuration of ions. Okay, the exercise number 11 and 12 will be the same. Now let's move to the next exercise related to the predict the chemical formula. Okay, and the name of compounds. So you know that the elements prefer to form ions. Okay, for example, gallium, this guy prefer to form this one stay in the group of 3As. So this one prefer to form 3+. Okay, so you got a gallium 3+. Okay, fluoride stay in the group 7A. So fluoride prefer to form an ion of fluoride minus. It's okay. So when a positive charge, or when the positive ions of gallium 3+ and fluoride minus stay close together, electrostatic force will let two of them, or two ions here, bind together. Okay, but the rule is, because of gallium have a 3+, okay, so it means that the gallium ions have a capability to attract 3 fluoride. Okay, so gallium will attract 3 fluoride. So it means this guy will form a kind of compound with the structures of gallium fluoride 3. It's okay. So this is the reason, or this is the way for you to define the compounds come from different elements. Okay, gallium fluoride. The next one, lithium. Lithium stay here, hydrogen stay here. Okay, so normally lithium prefer to become lithium plus. Okay, but be careful in this case. Hydrogens, even they stay in the group 1, but this guy is not considered as a metal. It's okay, it's not considered as a metal. So hydrogen sometimes can accept 1 electrons to become the electron configuration of the stable guy is helium. So it means that now in this case you will have a hydrogen minus, and they will form a compound LiH. Okay, or the name of this one is lithium hydride. Okay, lithium hydride. Similar to the other case, aluminum and iodide, you will have a Al-I3. Okay, aluminum iodide. Potassium and sulfur, they will form a kind of potassium sulfide. It's okay. So it's based on the formation of ion you did from the last exercise. Okay, let's remember, for me, when two ions, when ions attract together, normally they need to neutralize charge. So it's the reason why 3 gallium or gallium 3+ need 3 fluoride minus to become a neutral charge of gallium fluoride, or GaF3. Okay. Okay, again, now you have to predict the compound is molecular or ionic. Okay, ionic compounds. So as the rule, ionic compound between metal and non-metals. So you have something contain the metal here. It should be ionic compounds. So you have this one, lithium, okay, scandium, cesium, and silver. Okay, so this one ionic compounds. The other molecular compounds are composed of the molecule contain non-metals. For example, in this case, boron, hydrogens, boron and hydrogen, they can consider as non-metal, right? Carbon, hydrogen, oxygen, they are non-metal. Okay. Nitrogen, oxygen, chloride, they are non-metal. Nitrogen, oxygen, chloride. Okay. Nitrogen, fluoride, nitrogen and fluoride. Okay, so this one, this one, this one, this one are molecular. Okay, ionic. Okay, guys. Okay, the next exercise. But I want to move to some more simple first before we go back here. So, okay, for example, exercise number 17, very simple. So you have oxygens. So the very first question related to write the full chemical symbol of 3 isotopes. So chemical symbols. Firstly, oxygen, we have the chemical symbol of O, right? Okay. And from the periodic tables, you know that oxygen stay here with the number 8 of the atomic numbers. So normally you write 8 in this position. Okay, now you have a 3 isotope. So let's write another oxygen 8, another oxygen 8. Okay, the number of neutron, the total number of neutron and proton will give you the atomic mass, right? So in the very first one, if you have an isotope with 8 neutron and 8 protons, so the atomic mass of the first case will be 60. Okay. The second thing. The second thing, you will have a 17. And the next thing will be 18. Okay, so let's describe the similarity and difference between 3 kinds of atom of oxygen here. Okay, so from this moment, from you at this moment, you have to only describe the similarities, is including number of protons, number of electrons, and the difference is the number of neutron. Okay, and also the mass, the atomic mass. The other difference in property of oxygen actually is not still stay in the how to say in the scope of the general chemistry one, because of actually different properties of oxygen 16, 17, 18 is quite hard for you at this moment. Okay. So this one will related to something like how to say some of the magnetic properties, some of the singlet, triplet oxygen, something like that. And it's a little bit complicated to use this moment. So the exercise number 18 will relate it to the molecular structure shown here. Okay, so you have on 5 structures. Okay, so now it's quite simple because of actually you have the name of the items. Okay, so the first one is the name of the chlorine gas. This is this guy, Cr2. Okay, the case of propane. Propane contains of 3 carbons and 8 hydrogen. Is the propane, and this one is represent to propane with 1, 2, 3 carbon 1, 2, 3, 4, 5, 6, 7. Oh, sorry, 5, 6, 7, and 8 hydrogens. Okay. Nitrate ions which have a structures of NO3 minus. So this one will contain 1 nitrogen and 3 oxygens. So this one is nitrate. Okay. Sulfur trioxide. The prefix tri here explain to you the number of 3. Okay. So sulfur trioxide will be SO3, and this is this one. And lastly, the methyl chloride, CS3, Cl. This is this guy, E. The last exercise here will related to calculation, some calculation, right? Firstly, let's understand the phenomenon up here. Normally, you have a process of burning some coal in power plant. Okay, so the process of burning coal in power plant actually is represented by a reaction carbon, oxygen to form CO2. Okay, but you see, because of there are some sulfur inside the coal, so you have another reaction, sulfur plus oxygen to form SO2. Okay, so to reduce the sulfur dioxide emission, so you see, the thing is, we let the emission of carbon dioxide, we only limit the emission of sulfur dioxide. So it's a little bit trouble, okay, but okay, it depends on the technology at this moment. So to reduce the sulfur dioxide emission, they use the calcium oxide. So it means that between between the sulfur dioxide and calcium oxide, it should have a reaction, right? And the reaction there will be right, CaO, calcium oxide, SO2 to form calcium SO3. Okay, and thanks God, because of all the equation here is balanced. It's okay. Question B. Question B related to if the coal is burned in power plant is 2,000 tons of coal per day. So you will have 2,000 tons of coal. Okay, and then you will see that actually because of the coal contains sulfur inside. So 2,000 tons of coal here will including carbon and sulfur. It's okay. So you know that the sulfur will take around 2.5% by mass. So you can calculate the mass of sulfur will equal to 2,000 multiplied to 2.5 over 100%, and you'll get this guy is around 50 tons, right? It's 50 tons or 200 tons, right? 550 tons of sulfur. It's okay. Okay. So for the reaction, you see in this reaction here, you have a 32 grams of the sulfur or 32 tons of sulfur will react with oxygen and form 64 tons of SO2, right? In the very first equation. In the second equation, you will see that 64 tons of SO2 will react with 56 tons of calcium oxide. Okay, and it will form how many? 120 tons of calcium sulfide. Okay, so the next thing, you have to calculate the mass of calcium oxide, right? So from the mass of sulfur of 50 tons, you can calculate the mass of SO2 equal to 64 multiplied to 50 over 32. Okay, and then you will get 100 tons of SO2. Okay, in the next part, the mass of CaO unit will be equal to 100 multiplied to 64, sorry, multiplied to 56 and divide to 64, and it's equal to, let's calculate to me. And then the mass of calcium sulfide equal to 100 multiplied to 120 and divide to 64, and it's equal to something. So, okay, guys. So let's go back a little to the exercise, okay, about the results. I believe you understand how to calculate it. This one is exercise from the high school. Okay, so for the exercise number 16 here. The first one you have to, let's understand, there are two types of arrangement of the atoms, okay, in bulk state or in the solid state, okay. So we have a loose pack arrangements like A or closed pack arrangements like B, okay. So firstly, let's consider that you are placed, or you make a monolayers of the rubidium atoms on the surface, okay, of a square with 1 centimeter on the side. Okay, it looks like you have a square, 1 centimeter, and you put rubidium atom there. Okay, you have to calculate the numbers. So you see in this one, the size of the radius of one rubidium, you see, half of this one, or diameter of rubidium, okay, is 4 angstrom. Okay, so when you set the atom there on the corner of square, and then you arrange the other on two sides, okay, so now you will have the numbers of the rubidium atoms, like in the arrangement A. This will be on one side, okay, on one edge. This will be 1 multiplied to 10 power minus what? Minus 2, right? Divide to 4.95 multiplied to 10 power minus 10. Okay, so by that, you will have the numbers of rubidium atom on one side. So if you need, and in that case, you have the same number of rubidium on this side. Okay, so this means that the number of rubidium on the square surface with 1 centimeter on the side will be square times of the, or the square of the first values you calculate, or this one becomes square. This is the number of rubidium atoms. Okay. In the second state, a closed packed state. Now you see, actually, the distance between, in the first case, the distance between two layers, okay, will be the same with the distance, will be the same with the diameter of rubidium atoms, okay. But in the case here, the distance between two layers of atoms will be shorter than the distance between, or shorter than the diameter of one rubidium atoms. Okay, so you see, actually we can see the angle here is theta t. Very simple to see that, right? So you will have the values of A. This means the distance between two layers of rubidium atoms will be A. Okay, A will be equal to cos theta, right? Multiplied to D. Okay, and this one will be equal to square root of 3 over 2 multiplied to D, or diameters here. Okay, so you will see A will be smaller than the diameters of the rubidium atom. Okay, so by that, if you set the arrangement here into the 1 plus 1 square, okay, 1 square, now you will have the number of rubidium in the arrangement B will be equal to 1 multiplied to 10 power minus 2 divided to 8, right? Of course, A here should be changed into metal, and the number of rubidium on that square will be square time, or power 2. Okay, so now you see, in the first case, you will have the ratio between the distance of two layers between the first case and the second case is a factor of square root of 3 over 2. So the factor to increase the number of atoms on the surface at arrangement B from arrangement A is the square root of is the reverse of that values. Okay, this is 2 over square root of B. Okay, and you see the B have a closer and higher numbers of atom compared to arrangement A. So it means that if you extend to 3 dimensions, the number of atoms in B will be much bigger compared to the number of atoms of rubidium in A. Okay, so the answer for the last question will be B will be, or arrangement B will be greater density compared to A. Do you get that? Do you have any questions, guys? I cannot hear anything.
No.
Because it was still very simple, right? So maybe several next chapter will be a little bit more complicated and you have to think something. But I think the first and the second chapter is too easy for you. Okay? So if you don't have any question, we can stop here. Okay? Thank you very much for coming.
Thank you, teachers.
Okay, you're welcome.
Goodbye, teacher.
See you.
Yeah. Goodbye, teacher.
See you.
Goodbye, teacher.